Thank you. Thank you all for the audience. So my paper has a it's different from the previous ones in this session, and is not a good way. I mean, we were not motivated by any application. It was directly in the statistical point of view. So let me move to the. So the outline is going to be like that. So I'm going to discuss some about our motivation, and then some definition, and we are going to move forward to what is the core of the presentation, which is dedicated to the deformed exponential functions related to those probability functions, and then we move to the aspects also to the statistical divergence, and the particular one we are working with, so it's the phi divergence, and then the existence of the conditions for existence of those connecting paths, and finally the discussions. So what's our basic problem actually, and our rationale in the point? So there is a class of probability functions called deformed exponential functions, or there are some different names in the literature, so phi functions or phi family of functions. And so the point is, as a very general model that we can make some parameters in order to fit more or less more wider or narrow class of distributions, we would like to find which are the conditions and necessary and sufficient conditions in order to connect two of those distributions in order to be what we call path connected, and still model a different distribution. So it's like, for example, we can put different, for the simplest case maybe, the normal distribution, the Gaussian one, we can combine those in a mixture of Gaussians. So we need to take care of the normalization factor in order that the integral should be 1 and so on and so forth. So here our problem is, okay, we are going to do the same for two different distributions, which are generating this aspect of being deformed exponential ones, but which are the connections? We cannot actually, in the geometric sense, combine them as we want. There are some constraints. That's what we are going to show here. So that's basically the main idea that I would like to keep at this moment. There is a possibility of connecting different distributions, and we are showing sufficient and necessary conditions for that. Okay. So there is a lot of math here. Of course, I'm going to skip the most important, not the important ones, but the boring details. So we are assuming actually a measure space me, which should be non-atomic, and then we are considering a set of all probability distributions lying over a manifold P of mu. Okay, and so this L0 denotes the set for all measurable functions over T, saying that all those functions should be probability distributions, should be have the integral equals 1. So what is a deformed exponential function is? Actually, it's quite simple. We are calling phi here. It's a mapping. Actually, it should be a convex function, and it should have some constraints. It should be equals 0 when the limit of the argument goes to minus infinity, and goes to is equal to infinity when the argument goes to infinity. So it's bounded between 0 and infinity. So it doesn't go to minus infinity, for example. So these are general definitions and some examples to make them simple, at least simpler. So these are some functions that are cases, special cases of deformed exponential functions. The first one is called the kappa exponential function. It has such form. It's called exp of k. This index k means that it's different from the regular exponential. So it's funny because for a given argument for kappa kappa equals 0, so it's the regular exponential. When it's not, so when it's different from 0, so we have a more fancy expression. We have also the Q exponential function. Some of you that are aware of the Thales entropy, for example, it's based on that. So it's a different also, and provides a nice properties with those. So it's Q exponential has this form for Q greater than 0. And it's equals 0 if U, the argument, is lower than this quantity related to, of course, the exponent Q. Okay? Another one is called phi exponential function, which is the inverse of that one. So it's a definition of an inverse, actually, which is somehow expected in the sense that we know the relationships between logarithm and exponential. So these are some examples. And what we would like. Okay, let's imagine that we assume that now we have two distributions, P and Q, that lie over the manifold of the distributions that we are working with. So the question is, if we map those, or actually we are going to construct a phi1 over phi2 path, or phi1, phi2 arc, in such a way that we can connect those and become the, making that as a new distribution. Actually, it's going to construct a new one. It's in the case that we do, for example, for a linear mixture of Gaussians, we actually construct a new one. So we have this mapping, and actually the curve is defined like that. So we have phi1 and phi2. They are inverses. And we have also this important term here, which is the kappa of alpha, which is inserted in such a way that the integral should remain as a probability density function. Okay? So we are going to use the word phi path instead of phi1 and phi2 for the case where we are considering the same mapping for both distributions. So exponential path, which is a very regular one in geometry, is when we consider that the phi functions, phi1 and phi2, is the regular exponential, and we are considering, let me get back a little bit, so that that function u, it's 1. It's a constant one. Okay? So in the previous GSI in 2015, one paper from Miguchi and Komori, they have actually analyzed the case where u1, u0 is still a constant, is 1, and they have the a very simple case where the functions are the same. Okay? So in their work, they have concluded that unless, for that case of u0 equals to 1, unless the functions are equal, so there is no path connecting two different distributions, that there is still a new distribution over the same probability, the same manifold of the probabilities, the same p mu. Okay? So let's move a little bit further. So that our motivation was based on that paper and thinking, okay, can we do a little bit, let's go further if the functions are different in that sense. So actually, our idea was based on the thinking a little bit of how to write that kappa function, which is getting back here, is written in terms of the alpha parameter in order to normalize the functions. So we can actually write those, but it's going to appear as the kappa of alpha equals to 1 and kappa of alpha equals 0, and still the need of u0. Because in that sense, if the functions phi1 and phi2 are different, so we cannot rely anymore for the constant case of u0. Okay? So let's say the tricky part is that kappa function, we can show, actually it's shown in one of our papers from the entropy last year, that we can write the divergence between two different functions with an exponential alpha, which is related like that, is related to the general function for the alpha, for any value, and for the 0 and 1 values here. Okay? So, the interesting part, and really, it's not a coincidence, of course, but it's really interesting that if we consider, as in the Eguchi and Komori paper, that the functions are equal, but more than that, they are equal to the exponential, which is the simpler case. Simplest case, actually. So, and the function is constant as their case, so we are going to reduce that divergence, which is very general, to the Renyi divergence, which is a more, let's say, more general divergence than, for example, the relative divergence that's defined by Shannon, or the Kullback library also that we can use, okay? So, even for that case, this kind of divergence can be seen as a generalization of the Renyi divergence. So this was a very interesting result, at least from our point of view, that we could generalize the idea of divergence for a wider range of distributions that rely on a curved space, for example, over a P of mu manifold. So if we move forward analyzing the limiting cases, so we are going to have the the divergence for the function phi. For alpha 0 and 1, we are going to be working on those limiting cases, which is nice. But in this, is reduces to the phi divergence, which was proposed by me and my colleagues a few years back in 2013. That is some kind of that. That's the general expression. If you replace phi as the exponential one, we are going to reduce to the Kullback library divergence. Okay? So we have some properties here that we need to describe. So for 0 and for 1, it is actually the same for those. So the limiting cases is the, let's say, the simpler one, or the most known one. Okay? So here's the reference of the paper where we proposed that divergence. And then, again, if phi is exponential and u0 is 1, so that's important. That u0 is very important. So we reduce to a particular case, which is very well known in several communities, for the Kullback library divergence. Okay? So, but again, we are trying to connect different distributions, and we know that we can relate them regarding the divergence between the difference between those. So the question, actually, the motivation for that paper, what are conditions? What are the conditions for phi1 and phi2 that they need to satisfy in order that distributions P and Q, they could be phi connected, phi path connected, or is there any, in another way of asking, is there any kappa of alpha that exists in order to perform that? So the answer is yes. Of course, it's not any given distribution or any given set. The complete answer is given in a series of proofs of those propositions which are in the paper. And so actually, let's just going through some of those. So let's, what we need to provide is that a phi function should be bounded for a given alpha when we wait for a given u of 0. So again, this u of 0, u0, needs to be non-constant, actually. Okay? And of course, the distribution, the integral also for the phi2 needs to be also bounded. More than that, the relationship between those two functions need to respect that inequality. So a given alpha, which is the argument of that kappa function, should be weight the phi1 and be still lower or equal than the application of the function over the same set of lambda u of t. Okay? And as a final, actually, not result, but consequence of that is that the functions hold actually one of the possibilities is that if we are working on the sup, on the limit of the sup for going, the argument going through infinity, so this actually taking into account that lambda 0 needs to be smaller than the infinite. It means that it should be bounded for a given lambda 0 also in order they can be path connected. So this happens, for example, if they are equal and they are the exponential, which they converge actually for the point. So, but one function that is deformed, just an example that this is an important result because not all deformed exponential functions can be path connected. So this is one example. So if we take into account that phi function, for example, the same one, phi1 and phi2 are equal, but they are in that sense. So we are not going to satisfy this equation, inequality actually. So we are not going to be able to connect any of those. So in order to, final slide, in order to be path connected or arc connected, any deformed exponential functions should have some conditions on the u of 0, which is related to the normalization of those distributions. By the way, tomorrow we have another presentation, which is also, again, in that line of more theoretical aspects, where we discuss the importance of that U0 for different kind of distributions. And more, so those phi functions, phi1 and phi2, they need to respect some necessary and sufficient conditions in order to be able to be, again, a new distribution. Okay? So, here in this work, so that's the conclusion. And some perspectives, which we think that's, we have assumed that we are considering a non-atomic case. So what happens in the atomic one? So when we wider the field of distributions, and in a more imminent step is to evaluate the geometry actually, to verify the geometry of those kind of distributions in order to make those more, let's say, application-oriented in some sense. Because so far it's very, as I said, it was not a good advertisement saying it's very different from the previous ones, but it's more on the theoretical side. And then we are going to check whether, just going back, whether this divergence can provide any gains comparing to the other ones. Of course, we are going to have to be careful about those definitions of the phis and the u's and so on and so forth, but we believe it's a promising way to go forward. So thank you, and okay, thank you.
One application that I see is when you want to simplify a distribution, approximate a distribution by another simpler distribution. And this happens very often in many areas, and in particular in Bayesian inference, when you have for example, a joint distribution of two variables which are related, and you cannot do any computational fast. So you want to approximate it by product of two distributions in such a way that you can do the computations in an approximate way. In those cases, very often we need some criterion to measure the distance between the two distributions. Now the question is, does this divergence or this criterion is easier to optimize in some classes of the probability distributions or not? This is the point.
Thank you, and that's a very good question. And actually, the answer is going to depend on, of course, what the choice we are going to make. For example, as I said, phi can be exponential, and then we resort to the Kullback-Leibler one. But we need inverses and then the derivatives, which is the prime one. And so, in order to make a fair comparison, we need to know what kind of distribution, what kind of function you are going to set up here. And of course, the choice of phi implies in some choice of u's, zeros as well. So I don't have let's say, a definitive answer because it's function dependent in that sense. So, but of course, this is going to be a concern in the sense that for more practical approaches and more practical applications, the choice should be also driven by the simplicity of the computation.
Thank you for the talk. I wanted to ask you if you can give some intuition, if it's possible, or can you explain on your condition for what's going on when you approach in the denominator when you're lambda 0? Is that some type of density around a point or something like that going on?
Thank you. You mean for the limiting cases, right? Yeah, that's exactly what they're saying. So we are actually, when you apply, it's like the point, because each point now is a distribution one. So the distribution is approaching or going far away from the manifold. So it's in the limiting cases, you are going far away or going too close to the manifold of the distributions. So it's yeah. Okay. Yeah. Yes. I mean, in that sense, sorry, I was misunderstanding. So in that case, it's actually an application of the limit for the function. So these are functions that you are going to need to. They cannot explode actually. So they need to converge to a given value, which can be quite high, but that's the point. So it's let's say we need to evaluate for each case in order to see whether we have a bounded value or not. Okay.
So in your talk, you made a very how do you say it? You had a nice main result, a very concise check, basically, for the connectivity between two probabilities. I'm wondering how this characterization and this connectivity will help you to get a grip on the geometry in plan that you had on the future work, to get a grip on the geometric. Is it with generators, or how are you going to proceed? Because now you have connectivity and geometry. Okay, it starts with connecting curves, but then what would be the next step? How would you use your results to take that next step?
Thank you. Again, we are going to, for example, it's complicated in this some sense that for those functions and for those results, convexity, of course, there are some background stuff that I'm not talking about for convexity, monotonicity, and so on and so forth. But what seems easier, at least that's what we are focusing on right now, is to start from those divergences that we can actually use those equations that we already know to write something about the functions that we need to describe. And so for the divergence cases, we have a lot of, let's say, results from the geometry aspects that we can take profit from. So that's, let's say, our intuition, it's pushing us in that direction. Of course, it's still an ongoing work. I didn't mention, but my colleague Rui is also a professor in the same university, and Luisa is our PhD student, so she has a lot of work to do from now on. So, but to wrap up, for the point. So our idea is to start from the divergence aspects and then go further with the geometric ones to have some insight from the other points. Okay, thank you.